Okay. Okay, so we are talking about basis and dimension, I believe, still. Okay, so let's just remind ourselves of what we were talking about last time, right? So we left off, we were talking about, so what section are we in? I'm gonna check. Is it 4.3? Anyways, okay, I'm sorry, I forget the section number, 4.3 question mark. So we have a notion of basis and also dimension. So a basis is going to be a collection of vectors from our vector space, right? Such that the collection spans the entire vector space. So the span of these guys is equal to V, and the collection itself is linearly independent. Okay, that's a basis. And then dimension is going to be the number of vectors in a basis. This is, so it doesn't change depending on the basis. The number of vectors doesn't change. I'll just put it that way. Okay. All right, so last time we showed that the following, so this collection 1, x minus 1, and x minus 1 squared was a basis for P2, right? So we showed that these were linearly independent and their span was all polynomials of degree 2. Right. And notice that this has three vectors in it, right? We also know that P2 has a standard basis. So the standard basis for P2 is the collection, we'll just use A for this one, 1, x, and x squared, right? This also has 3 vectors in it, right? Okay, so we can see it should always be 3 vectors for any basis of P2. That has to stay the same, okay? So for example, without even checking, we can say that this collection 1 and x plus x squared is not a basis. We know this because this does not have 3 vectors or polynomials, right? We can verify this using the definition by demonstrating something that's not in the span of this, but is in P2, right? So if we look at the polynomial, let's say 1 plus 2x plus 3x squared, right? This is not in the span. How did I put this? Yeah. Of this, right? And it's because, well, we could write 1 plus 2 times x plus x squared, but that doesn't give us the proper coefficient in front of x squared, right? And then if we try to write, we'll multiply that by 3, then we don't get the proper coefficient in front of x, right? So we can't write Q as a linear combination of these two polynomials. So it's not in the span, meaning that this set does not span P2. So cannot be a basis. Right? And as another example, if we look at the collection 1x, x squared, and let's say 2 plus 3x squared plus, oops, I wanted 4x plus, that's fine. Okay. This guy right here, this has 4 vectors in it, or 4 polynomials in it. So we already know it can't be a basis because it doesn't have the right number of vectors, but also notice that, wait, so let me first say, this is not a basis. And what would be the reason why this would not be a basis?
The vectors are not linearly independent.
Yeah, exactly. So it's the other part of the definition, because these are not linearly independent. So Li stands for linearly independent. Because that last vector we can see is a linear combination of the others, right? Okay. So we have for P2, we have 2 examples of a basis and 2 examples of things that are not a basis, right? Okay, cool. So let's see. This, just to compare, so there is an example in the textbook. In RN, or sorry, not RN, R3, right? Where they look at some collections. So here we have it's just these 4, 5, 6, I believe. And I'm going to try and fit them all on one line. Oh, oops. Okay. Here we go. Oof. Okay. Here's 1, 0, 0, 2, 3, 0, 4, 5, 6, 7, 8, 9. There we go. Okay. So we have these three different sets of vectors from R3, right? So I'm going to actually draw lines between them so it's clear what we're looking at. So here are our three different sets. This first one cannot be a basis, right?
It doesn't span R3.
Yeah, does not span R3. And if we skip over to the last one, this cannot be a basis. And that is because these are not linearly independent. Okay, and you could see that if we were to put these into a matrix and row reduce it, we would necessarily have a free variable, right? So these could not be linearly independent. And the ones in the middle, these, so this collection in the middle, geez. Oh my God, okay, here we go, there we go. This is a basis for R3 because it will be both linearly independent and it will span R3. Okay, so this is similar to, so compare this to the previous example in terms of polynomials, it's essentially the same ideas, right? Okay, so there is this correspondence between R3 and P2, the polynomials of degree 2, right? They're both three-dimensional vector spaces, and we'll see that finite dimensional vector spaces are essentially like Rn, right? There's not really a big difference in terms of the linear algebra that we do on them. There is a difference in terms of how we interpret the vectors themselves and ways that we can use them, but yeah, when we're doing linear algebra, when we're like doing computations and those kinds of things, these are essentially the same. Finite dimensional. I've not yet defined that, but I will later in the class. So I will just, I'll define that later. Okay. So let's see. We have the following theorem, which is called the spanning set theorem. Okay. So suppose we have, is this part of section 4.3? I believe it might be from section 4.4, what I was talking about. Oh, do you mean the spanning set theorem?
Yeah.
Yeah. I believe it's part of section 4.3. I can check really quick. Yes, it should be. It's theorem 5 in 4.3. Okay. And so this says that if you have a set, which we'll call S, of vectors v1 up to vk, so suppose S is a set in V, your vector space, and H is equal to the span of S. So it's the span of those vectors. Then we can say two things. So first of all, if VI can be written as a linear combination of the other vectors, then if you look at the span of S with, how do I say this? S minus VI, meaning the set where you take out VI and you have everything else. The span of that will be the same, or will still be H, right? So it will still be the same thing as the span of S. So it's just saying that if you have something that could be written as a linear combination of the other vectors, it's not necessary in the span, right? It'll still span the same thing if you pull it out as if you left it in, right? Okay. And then related to this is that some subset of S, it could be the entire thing or it could be smaller, is a basis for H, right? Okay. And the idea is that you just throw away the vectors that can be written as linear combinations of the others.
I have a question. Oh, sorry.
Go ahead.
So I feel like sometimes the textbook uses wording where it says like the vectors that can be written as linear combinations of the preceding vectors. Is that important or not really?
No, I think that's just a wording thing. The preceding vectors. Interesting. Yeah, no, I mean, I guess it's just referring to the ones other than VI, right?
So like it's referring to vectors v1 through vi minus 1. And it's saying that if...
Is it in a particular spot?
I feel like the textbook uses this wording a lot. I'll get back to you.
Okay.
But I feel like in situations like this, they would use that kind of wording.
Right. Sometimes it's nice to refer to like writing. So what am I trying to say? Sometimes when we're doing a proof, like keeping track of, or sort of moving along your set of vectors in a particular way means that you can like keep track of like what you're doing.
Yeah, so you know which one. Okay, they do use no, okay, they use the word remaining vectors in here. So I guess it's just like you said, just a way sometimes to keep track of which ones to throw out.
Right. Yeah. Yeah. Okay. So essentially, so like I said, for part 2, it says that some subset of S is a basis for H, and you would get that by throwing away those extraneous vectors, the ones that can be written as linear combinations of the others, and you know that you can do that by part 1 of the theorem, which tells you that if it can be written as a linear combination of the others, it's not necessary in the span, right? So basically the spanning set theorem, so I guess I'll put it this way, essentially the spanning set theorem tells us that any spanning set can be turned into a basis by throwing out the unnecessary, I'll put this in quotes, unnecessary vectors. And to be careful, you should do this like this throwing out carefully, like don't throw out everything all at once. Yeah, but it's good. Yeah, this is essentially what the theorem is telling us. Okay. So we can get a basis from any spanning set. Okay, and then there's one more thing from this section that I wanted to go over. We'll call this a lemma. We're not going to prove it, just like we're not going to prove the spanning set theorem, although you can see the proof in the textbook. Okay, and so this lemma says that if you have a collection of vectors, and these are linearly independent, and you have another vector, which we'll call u, which is not in the span of v1 up to vk, right? So we have these two things. Then if we tack on u to this collection, so if we look at u and v1 up to vk, this is linearly independent. Right. Okay. So the idea is if you have some linearly independent vectors, just pretend these are linearly independent, right? So you've got your v1 up to vk, and you have a vector that's not in the span of these. So you have some u going in some other direction. Then if you look at them all together, they will still be linearly independent. Right? If you add one more that's not in the span, you preserve your linear independence. Okay. So like I said, we're not going to prove this, but if you want to, you can try to prove this yourself. So you'll want to work from the definition of linear independence. Okay. Okay. But we are going to be moving on. So I really would like to get through chapter 4 pretty quickly. So I think it's more important that we get to the next chapter where we'll talk about eigenvalues and eigenvectors. Those are really important and useful. So I might move through the next few sections a little quickly, but we'll see. Okay, so this is on section 4.4, which is about coordinate systems. So we've talked about coordinate vectors in terms of a basis, right, earlier in the semester. So we're going to kind of review that and also talk about this in terms of our abstract vector spaces, right? Okay, so the first thing is this unique representation theorem. And what this says is that if you have a basis for your vector space, so say we have B, is a basis for V, then for each vector in V, so for each vector X, there exist unique scalars C1 up to Cn such that X is equal to this linear combination. So C1 times B1, C2 times B2, up to Cn times Bn. Okay. Right. And so the important part of this is that these are unique, right? If this forms a basis, we know that X can be written as a linear combination of these because it will, the basis should span all of V, right? So what this is saying is that this representation in terms of these scalars is unique, right? And the proof is not too bad, so let's just go through it quickly. Okay, so such a linear combination, or let me put it this way, such scalars C1 up to Cn exist because the basis B spans V, right? So we know that we can write X equal to this sum right here. So we want to know whether it's unique. So how we go about this is we suppose we have another set of scalars let's say D1 up to Dn such that X is also equal to this linear combination. Okay, then if we look at those two representations of X, they should both be equal to X. So we're going to subtract one from the other. So we have C1 times B1 up to Bn minus D1 times B1. Oh, wait, okay. B1 up to Dn times Bn, right? So on the left-hand side of this equation, we get the 0 vector because X is equal to X. On the right-hand side of the equation, we can group these by the vectors. So we would get C1 minus D1 times B1 all the way down to Cn minus Dn times Bn. And if this is equal to the 0 vector, on the right-hand side, we should have each of these scalars being 0, right?
Oh, so since like B1, B2 are like all linearly independent, none of them can be the 0 vector, right?
Yeah, exactly. Yeah. So yeah, that is an important point. Note, since this is linearly independent, none of these are equal to the 0 vector. Yeah, so we get that C1 is equal to D1 and C2 is equal to D2 and C sub n is equal to D sub n, and all of those scalars are the same, meaning that this representation is in fact unique. So let's just say, therefore, the representation is unique. Okay. And the importance of this, of the fact that we get a unique representation from a basis, is that we can interpret these as coordinates. So we can interpret these scalars these unique scalars as coordinates, which are determined by the basis. So for example, going back to P2, we know this has a basis 1 x squared, right? And if we look at P of X, that looks like this, right? 5 plus 2x plus 3x squared. So the coordinates or the scalars that describe this polynomial, we would call this one C1, this guy C2, and this one C3, right? Those are the scalars, and that's a unique representation in terms of the basis. So what we could do is then form a vector that would be those scalars, right? So we would just put them into a vector. So we would get 5, 2, 3, right? So that's what I mean by interpret them as coordinates, right? So we use those as the coordinates and we form a vector out of them, right? Okay. And so more generally, if you have a basis, if this is a basis for V and X has its unique representation like this, then the B coordinate vector of X is going to be, so we're going to use that same notation we were using before. So we put the bracket and a subscript B. This is just the vector of those scalars. Okay. Okay, so in terms of this example right here, we would write this P sub B, right? That's its coordinate vector. Okay. So we can consider so moving from your vector X in your vector space to its coordinate representation, we could consider that as a transformation, right? So the mapping which takes X to its coordinate representation in B is called the coordinate mapping. So it goes, so its domain is V, your vector space that you started out with, wherever X is, and the codomain is Rn, where n is the dimension of V. So this is assuming that the dimension of V is finite, but yeah. We do get this. This is called the coordinate mapping. Okay. Yeah. And this is determined by the basis. B, right? Okay. Now, this map, we will not check these things, but they are true. This map is linear. It is 1-to-1, and it is onto. Okay. So, in particular, this is what is called an isomorphism. So just to write out what that is. So a linear transformation is an isomorphism if it is both one-to-one and onto. Okay, so remember those are two separate properties, and it could be one-to-one and not onto. Transformation could be not one-to-one, but it is onto, or it could have both properties, or neither, right? So there's different combinations of these, but if it does have both properties, we have a special name for that, and that is an isomorphism, right? And what it means for there to be an isomorphism between V and the vector space Rn is that these are essentially the same as far as linear algebra is concerned. So if there exists, let me put it this way. We'll say T from V to Rn. These are the same So I'm talking very loosely here, so I'm going to put this in quotes, but right, it's just saying that the structure of those spaces is the same, right?
So when you say these, you refer to V and Rn, just to be specific.
Yeah, V and Rn, yes.
Thanks.
Okay, yeah. So what this means is that all finite dimensional spaces are essentially like Rn. We don't really have anything that behaves differently than Rn as far as linear algebra is concerned, right? So these vector spaces that we've been talking about, these finite dimensional ones, when do I talk about finite versus infinite dimensional? Maybe I'll just define that now. So finite dimensional means the number of vectors in a basis is finite. Right, so we've seen plenty of examples. Of course, Rn is an example. And then any of your polynomials of degree n, that's an example. And then we've seen some other examples as well. Otherwise, we say that the space, so the vector space V is infinite dimensional if it's not finite dimensional. And an example of an infinite dimensional space would be all polynomials, right? So polynomials of any degree would have an infinite basis, right? So, or a better way of putting that is that it does not have a basis that is finite. So it will be infinite dimensional. Okay. Great. Okay, and so the benefit of having this, of knowing that we can write down coordinates in this way, is that it does make working with some of these abstract vector spaces a little bit easier, because we can then use the techniques that we've been using in Rn. So for example, If we're looking at some polynomials in P2, and we want to show that, so let's say we have the following polynomials. And P3. Minus 2t plus 7t squared. So if we have these polynomials and we want to show that these are linearly dependent, we can first write them as vectors and then, so write them as vectors using coordinates, and then we can try to decide whether they're linearly dependent or linearly independent, right? So usually when using polynomials, it's easiest to use the standard basis, right? Then we can just use the coefficients, right? So we're going to use the standard basis, then rewrite each of these in terms of b, so in terms of the coordinates. So for P1, we have 1, 0, 3, right? That would be the vector describing that one. For P2, we have 3, 2, 2. And for P3, we have 0, minus 2, 7. Okay. And then how we decide whether or not these are linearly dependent is we just put them into a matrix and row reduce, right? So when we do this, we get, here we do row 3 minus 3 times row 1, and we'll get negative, wait, 3, 2, 7. Okay, I'm just doing something strange. Okay.
So replace row 3 with row 3 minus 3 times row 1.
Uh-huh.
So then that would be negative 7, right?
It would be. Okay, that's fine. Okay. Yeah, there we go. Okay, and then row 3 is a constant multiple of row 2, so it will go away. Great. So this is the row echelon form, and from this we can tell that we have 2 pivot columns and 1 column that is not a pivot, so it corresponds to a free variable. Right?
So that means the columns are linearly dependent.
Mm-hmm. Yeah, free variable. So columns are linearly dependent. And from this, we can conclude that these polynomials are linearly dependent in P2, right? So we can just convert everything over to coordinates and use the standard methods that we've been using. And whatever conclusions we make there will also apply to the original problem, like before we put it into coordinates. Okay, so it can make some of these questions easier, right? So it's easier to deal with the vectors than to try to figure out if they're linearly dependent by just looking at, I don't know, and some of the methods that we were using before. Okay. Right. So there is a particular matrix. So in Rn, we can have this change of coordinates matrix. which might make finding the coordinates of a vector in a new basis a little bit easier, right? So in Rn, if we have a basis B, and we're looking at X, a vector in Rn, this is equal to this matrix formed by just putting those basis vectors into the columns, right? So we just, we stick these into a matrix, right? And then this will be equal to, so the original vector X will be equal to that matrix times the vector X in the B coordinates, right? So the B coordinate vector of X. Okay, so this thing right here, we use the notation P sub B, and then this is the change of coordinates matrix.
Can I ask why we write it with P, or is that one of those things where we just do?
It's just like someone started doing it, and I guess that's how it is. Like,
Okay.
Yeah. So, okay, so just to see why this is the case, we can write out what this is, right? So this equation is
It's just basically matrix by vector multiplication.
yeah, exactly, yeah. So if we look at what would happen if we multiply out this side, this is going to be, right? So the B coordinates will say are C1 up to Cn, right? And we know that the matrix multiplication, we can do it column by column. So like we would get C1 times B1 plus C2 times B2 up to Cn times Bn. And this was the definition of the coordinates, right? So these are your coordinates. So this matrix is your representation in terms of B. Okay. So what we have, just to copy down this equation down here, we have X, we have this matrix P sub B, and we have that multiplied by the coordinate vector, the B coordinate vector. So if we want to compute B, we could rewrite this as, or if we want to compute the B coordinate of X, that's the same as multiplying by the inverse of this change of coordinates matrix. So multiplying our vector, our original vector, by the inverse of the change of coordinates matrix. Does that make sense? Okay. So, yeah, this is, first of all, note the matrix P sub B is invertible. Why? Why is it invertible?
Is that because it corresponds to an isomorphic transformation? Are you allowed to say that?
There's a little bit simpler of a way.
Oh, it's because the columns are linearly independent.
Yeah, the columns are linearly independent.
Oh.
They come from, yeah, they come from a basis, which will be linearly independent, right?
And we know that the matrix PV is necessarily square.
Right. Yeah, because it will be, I mean, maybe it's not obvious right away, but they will be vectors in Rn, and there should be n of them in order for it to be a basis, right? Okay. Right, so this is linearly independent, and so let's go ahead and do an example where we're using this. So for example, if we have, so find the b coordinate vector of x where x will be -2, 1, so it's a coordinate, or so it's a vector in R2, and the new basis we want this in terms of is 1, -3, and 2, -5. Okay, so we're going to do this using this new change of coordinates matrix. So that will be equal to just the matrix 1, 3, 2, -5, right? We do want its inverse, so let's compute the inverse. So we get 1 over the determinant. The determinant of this matrix is -5. I'll just write it out. -5 minus -6. Right? So actually this simplifies to 1. And then we swap along the main diagonal, right? So we get -5 and 1. And then we get -2 and -3. So 3 for the other corners.
I thought we had to do, like, to get the inverse, we had to do 1 over the determinant times the adjugate matrix.
Yes. And
is this
is the adjugate actually.
Oh, okay. Oh wow, you're very fast.
So okay, so for 2 by 2 matrices, A inverse is equal to 1 over the determinant of A times, if A is equal to A, B, C, D, it's equal to DA minus B minus C. And I just memorized that.
Oh, okay. I remember now. This was from way back.
Yeah, it was a long time ago, yeah.
Okay,
So this
thank
other
you.
matrix, D, -B, C, -A, that's the adjugate?
Yeah, it is actually the adjugate. It ends up being like very simplistic because your like smaller matrices that you get are like just one. They're those like 1 by 1 matrices, sort of like degenerate. Yeah, but you can't interpret this as the adjugate. Okay, so yeah, this is just 1. So our inverse is -5, 3, -2, 1, like this. And to get our coordinate vector, we just multiply by this on the left, right? So that part's important. So we take this times our vector x, which was -2, 1. And we get -10 minus 2 and -6 plus 1.
Pardon me. It would be 10 plus 2?
Oh,
Because you
10. Yeah, it would be 10 minus 2. Yeah. Right? Yeah. Okay. So this will be 8, -5. Okay. What time do we end again? It's 1:50. I'm never gonna learn this.
And at
That's right.
1:50, yeah.
Okay, 1:50. Okay, cool.
Mhm.
So I think we're going to move on to section 4.5. Yeah, okay. Or do I want to do an example? No, we'll just, okay, we're gonna move on because we want to finish chapter 4. Okay. Okay, so section 4.5 is on dimension, which we've already been talking about, right? So some of this we've discussed prior to this, but okay, the dimension is the number of vectors in the basis. We've gone over that at the beginning of class, so I won't put that down again. Oh yeah, we also talked about finite versus infinite dimensional. And so if everybody's clear on that, we'll just move past that. So for dimension examples of dimension of different vector spaces, we'll do a couple. So a subspace of Rn is a vector space in itself, right? And so if we look at the span of, say, these vectors, right? Well, this is a subspace of R3. We can see from inspection that these are linearly independent vectors, right? So I hope that part is clear. So this means that this is equal to the span and that this is also a basis. So these two vectors together form a basis of H, meaning that the dimension of H is 2. And so what that means is that H is a plane inside of R3. It is not equal to R2, right? It's made up of vectors in R3, but it is isomorphic. Now that we have this terminology, we can say, and it's isomorphic to R2, right? So it is essentially like R2, but it's not exactly equal to R2, right? Okay. So that's one example of a two-dimensional vector space. We could also look at the collection of 2x2 matrices, right? And this has a basis of, we could just write these down. So the following, so we have these matrices, so just one at a time. We have 1 and zeros in all of the other entries. And so we'll need 4 of them to span the whole space, right? And then it's pretty clear that you could write any 2x2 matrix as a linear combination of these. So they do span this space. And also showing that they're linearly independent isn't too hard either, right? So these are, or we'll say, this is linearly independent and spans this space of 2x2 matrices, right? Okay, so there are 4 matrices in this basis. That means that this space M, the 2x2 matrices, This is 4-dimensional. Right? Okay. And let's do one more example. So we could look at the space. So this will be a subspace of P2. And this will be the set of polynomials of this form, x plus x squared, such that a and b are scalars. Okay. So this is a subset of P2. And another way we could write this, right, so is as a span, since it's just the collection of all linear combinations of these two polynomials. It's the same as the span of 1 plus x times and x plus x squared. Right? Okay, and then so we have something that spans this. If these are linearly independent, then this is a basis, right? So we just want to check that 1 plus x and x plus x squared are linearly independent, right? Okay. And we don't have to go through a bunch of work for this because, in fact, when you're checking that two vectors are linearly independent, you just need to check that one is not a constant multiple of the other, right? So it's easy when you have two vectors. When you have more than that, it gets more complicated. But yes, this is true because one is not a constant multiple of the other. Okay. Okay.
Pardon me.
Yeah, go ahead.
What do you mean by saying that it's true?
We were checking that these are linearly independent.
Oh, okay. Sorry.
Okay, yeah. So yes, they are linearly independent. Oh, yeah, so checking this. So this set 1 plus x and x plus x squared is a basis. So the dimension of H is what? Does anybody know?
Is 2?
Is 2. Yes, exactly.
Sorry, yes, that was my answer. Is 2 the number?
Yes. Right, because there are two elements in the basis. Okay, right, so this is dimension in some different contexts, and let's talk about a couple of results we have. So first of all, if we have a basis of V, so okay, if V has a basis B, and we have a collection of vectors v1 up to vk from V where k is greater than n. So we have a collection of vectors and the number of those is greater than the number of vectors in the basis, right? Because we used, so n is the number of vectors in the basis. So if we have this, then this collection, V1 up to Vk, must be linearly dependent. Oh, whoops, not independent. Great. Okay. So we aren't going to prove this. I think we may have proved this for Rn earlier, but essentially we have that our maximal linearly independent set has n vectors, and if we have any more than that, we can't have linear independence. We can't maintain linear independence. That's the maximum number that we can have and still have that linear independence. Right. And then, so we're not going to prove either of these. This says that if V has a basis B, and H is a subspace of V, space of V, then we can find a basis for H. So we'll call this A of vectors A1 up to AK, such that K will be less than or equal to N, right? So this means in particular that the dimension of this subspace is always less than or equal to the dimension of the larger space V, which makes sense, right? If it has to fit inside. Okay. Yeah. So something to note, maybe this might be interesting, is that our definition of in or like by our definition of dimension, the dimension must always be an integer. Right? So when we define it this way, it's just the number of vectors in the basis. It has to be an integer. There are other ways of defining dimension which allow you non-integer dimensions, but they're not very compatible with linear algebra. So yeah, something to note. Okay, and then discussed in this section is also null space and column space. So I just thought we would do a little bit of sort of review of that. Since we have talked about null space and column space before, but maybe it's good to go over it again. Okay. So here we have that the yeah. So first of all, the dimension of the null space dimension, which we called the nullity, right, of a matrix. So null space and column space of a matrix A, right? This is the number of free variables of the system AX equals 0, right? Okay, and the dimension of the column space and remember this was called the rank, is the number of pivot columns of A. Okay, so this is these two notions. Now let's look at an example of a particular matrix. So we have 1, minus 2, 1, 3, minus 4, 8, 0, 2, 2, minus 2, 0, minus 6. Okay, and so let's determine what the null space and column space would be and find a basis for those, since that's a common question. So what we want to do is row reduce, right? So that'll help us figure this out. So we're going to just start row reducing. So we can take row 2 and replace with row 2 plus 2 times row 1, right? And that would give us 0, 2, 2, minus 4. Yep. And then we can also do row 3 at the same time. So we'll do row 3 replaced with row 3 minus row 1. So 0, 5, yeah, 2. Negative 4. Wait, no. Wait.
Yeah, that looks right, I think.
Okay. Cool. And let's see, I can divide row 2 by 2.
I think it might just be easier
Uh-huh.
if you just subtract row 2 from row 3.
Subtract row 2 from row 3.
Yeah.
Oh, it might be easier, yeah. We'll try that. Okay.
I mean, it works either way, but
Right. Row 3 minus row 2.
Yeah, replace like row 3. Yeah, replace.
Yeah, then we would get 3, 0, 0. Yeah. And then we can scale row 3. In fact, I'm going to do 2 steps at once. So we're going to scale row 3 by 1, which gives us 0, 1, 0, 0. And then at the same time, flip.
Scale row 2 by a half.
Oh, yeah, that's nice to do too. So we should end up with 1, 0, 1, 0, 0, 0, 1,
Wait.
1, minus 2.
Oh, did you switch the rows?
Yeah, I did.
Okay.
Okay. And then I'm going to do row 3 minus row 2. There we go. Okay. That should be right. Okay, so we have 3 pivots, right? And so those are going to correspond to our pivot columns up here, which will be the first 3 columns. And so those are going to be well, first of all, the dimension of the column space is equal to the number of pivot columns, which is, this is the rank of A. So that's 3. And a basis for the column space is the columns corresponding to the pivots. So 1, -2, 1, 3, -4, 8, and 0, 2, 2. And then we have one free variable, right? So that corresponds to x4, right? So the dimension of the null space of A is 1, right? And if we want to figure out a basis, we do have to compute that. So in fact, it's just one more step for this to be completely row reduced. So let's to reduced row echelon form. So I'm going to go ahead and do that. And it would just be getting rid of that 3. And 0, 0, 1, -2, right? Okay, so this is A in reduced row echelon form, and to get the basis for the null space, we just solve the homogeneous equation, right? So we get x1 -2 times x4 equals 0, x2 actually just equals 0, x3 equals, or we'll write it this way, -2 x4 equals 0. So, and x4 is free. So our solution is the vector, we would get x4 times 2, 0, 2, 1. So our basis for the null space is just this one vector, 2, 0, 2, 1. Null space of A. Yeah. Okay, so yeah, we'll just end here. And then we will hopefully finish up with chapter 4 next time. And we'll see, we'll find out. But yeah, and then you guys should be preparing for the exam, which will be next Thursday. And I will post a study guide like the first time. So that'll be up soon. Okay, so I'll see you guys on Thursday. Also, we will have a quiz. And the quiz topic I'll put up on Canvas.
All right, thank you.
Okay, thanks.
Thank you.